Yeah.
Okay, Assalamualaikum and good afternoon. Can you hear me?
Waalaikumsalam, Prof. Yes.
Yes, we can hear you.
Right, okay. For these remaining hours, I will describe to you the final exam questions on Thursday and the past exam questions. So our exam will be on the 4th of July, okay, 2024, which is on Thursday at 9 a.m. Okay, so for full-time students, it will be at P16 BKT3. Okay, so make sure you all go to BKT3, not the previous test 1, test 2 at BKT4. So the BKT3 is beside BKT4. Okay, and for KL and Penang as well. Okay, at the respected center of learning. So the format will be format for the final. Okay, usually they have a part A. Okay, Q1, Q2,
Biasanya.
Q3. Okay, which is compulsory. Answer all. Okay, and part B, which is options. Okay, Q4 and Q1. Okay, so part 1 will be on the root locus and gain adjustment. Part 2 will be on, sorry, question 2 will be PID and tuning. Okay, part 3 will be the board plot and gain adjustment, which is compulsory. Okay, and part B is options, which is lag compensator or lead compensator. Okay, so either one, you choose question 4 or question 5. Okay, so so without any further ado, I go to the questions. Okay, which is this one, which is held last year. Okay, June 2022. This one is quite different because you have to answer all questions. Okay, so this session will be different. They give you options. So for this purpose, I would like to invite Aidil. Can you read the question for me? Question 1. A.
Okay, sure thing, Prof.
Question 1. A unity feedback system has open loop poles and zeros locations as listed below. Poles -3, -1, -3, and -8. Zeros 1 plus J5, 1 minus J5. Determine the following. The open loop transfer function of the system by incorporating a forward gain K. 2. The gain K for undamped response, the range of stability, and the JW crossing points of the system. And 3, the root locus sketch of the system.
Okay, so for question 1A, I share with my iPad. Okay. Okay. So you are given poles and zeros. Okay. Which is -1, -3, and -8, and +1 plus minus J. Okay. So this is given. So you are required to find the open loop transfer function with gain K. So very straightforward. Okay, just S -1 minus J pi, S -1 plus J pi, then divide by S plus 1, S plus 8. Okay, then you multiply all together. So you will get, sorry, your K is over here. K plus 26 divided by S cubic plus 12S squared plus 35S plus 24. Okay, so this one is the final exam. Sem 2, session 2022-23. Last session, eh? Okay. So we go to the second questions, which is the gain for underdamped response, the range of stability, and the J omega crossing. So for this purpose, you have to find the closed loop transfer function, which is TS. So as you know that TS is GS, 1 plus GS. Okay, so K and K in front of it. So you derive it. So you will get something like this. Okay. Then from here, you take the denominator. So you will get the characteristic equations, which is the S cubic. Then from here, you take the denominator. You get the. Then from here, you take the denominator of microphone, please. Okay. So this is your characteristic equations. And then plug into Ruth-Lewis table. Okay. So you will get 1. -35 minus 2K. 24 plus 26K. Okay. So this one, let it be as A, and this one is B, because you have to derive the A and B. Okay. So for A is where you use the determinant. Okay. Over. Okay. Then you will get A 396 minus 15K divided by 12 plus K. And B, the bottom one is minus 24 plus 26K 0. Okay. So divide by A. Then you will get B 24 plus 26K. Okay. So if we rewrite again, rewrite the Rolls-Royce table. So it will be like this. One, 35, and 24 plus 26K. And you insert this one, then you get, okay, the A and B. So the A is quite long, 396, 15K minus 2K squared divided by 12 plus K, 0. And 24 plus 26K. Okay. So the theory said that to find the range of stability, the first column must be greater than 0. Okay. The one that I mark, okay, is greater than 0. So 1 is already greater than 0. Then 12 plus K greater than 0. So K is equal to greater than minus 12. Okay, equation 1. Then the top one, 396 minus 15K, 2K squared greater than 0. So you simplify, you will get K less than 10.81 and K less than minus 18.31. Okay. I mean, you have two values. Yeah? The two values. This one is 2. And the last one is 24 plus 26K greater than 0. K is 923. Okay, so this is number 3. So from these 3 equations, okay, 1, 2, and 3, we can conclude that the range of stability is, okay, between 0, K, and 10.1, 10.81, sorry, 8124. Okay, so this is the range of stability. Okay, so the derivation is quite long, but you have to be resilient in order to find the solutions until the end. So to find the at J omega crossing, a J omega crossing point, okay, K critical or K marginal happen there. Okay, so we have to choose S square row at our hash table for even equation. So it will be 12 plus k S square plus 24 plus 26k equal to 0. Okay. So what is k critical? So from the range of stability, k equal to 10 point
8124.
okay is the k critical, right? And use this value, okay, use this value, insert inside this equation, the even equation, okay. Then solve for S, okay. So when you solve for S, so you will get S is equal to plus minus G 3.657, okay. So during the presentation last week, I already asked you the oscillation frequency, oscillation, how to spell OS, oscillation frequency, when K critical. So actually the value is from the crossing this one, plus J 3.657. We know that J is equal to J omega, J 3.657. So this J is the imaginary and omega is the oscillation frequency. Microphone off. 3.657 radian per seconds. Okay. And at this point, zeta is equal to 0, which is known as undamped response. Okay. Undamped response. As we look into the equations, find the gain k for undamped response. Okay, so the k is 10.81. Then the range of stability, 0, less than k, less than 10.81, and then the j omega crossing, which is 3.657, okay, radian per second. And after that, you plot the locus, okay. Locus. It's better for you to use different colors. Okay, you mark the zeros, the complex conjugate zeros. Okay. And then you mark the poles, which is -1, -3, -8. This one is a positive one. And J5 minus J5. Okay. So it is a third order system, if I'm not mistaken. It's a third order system. So we have 3 root locus paths. So first one will be this one. Okay. And then it will goes to here. Okay. The second one will be this one. And then it will go to here. And the final path will be this one, minus 8 goes to infinity without any friends, because there is no other zeros, okay? So we have 3 root locus paths as shown, right? So that is the question 1A. So let's go to the question B. Okay. So question B, I invite who's on the line? Oh, ramai ni. Hugh Huini. Hugh Huini.
Yes, Doctor.
Yeah, can you read for me question B, please?
A unity feedback control system is given in figure Q1b. The root locus of the system is shown in figure Q1c. The system is operated at 16.3%. Determine the following. The dominant pose and operating gain K at this point. The peak time, setting time, and steady state error for a unit step input. The range gain K for stability. Design a controller that could eliminate the steady state error as obtained in V2, but maintaining the same transient response. Validate the new steady state error after the implementation of the proposed controller.
Thank you very much. So now is the root locus and gain adjustment. So go back to the iPad again. Question 1B, where you are given open loop transfer function, which is GS KS minus 1 S square minus 2S plus 5. So the operating overshoot is equal to 16.3%. Okay. And you are given a plot, given the root locus plot, okay, using a graph there. Okay, so we have 2 paths. Okay, sorry, yes, 2 paths, which is over here. Okay, and zeros over here. Okay, I'm not sure about what is the J omega crossing. S square minus 2S plus 5. What is the roots? S square minus 2S plus 5. Can anybody press the calculator? S square 2S plus 5. What is the roots? Can somebody help me?
1 liter.
1. Huh? Betul ke? S
One,
square.
1 plus 2 I and 1 minus 2 I.
Thank you. Shukran jazilan. Okay. So now we are trying to find I'm trying to draw because you already have the drawing. So the thing is something like this. Then it goes here. Second one is like this. And it goes here. Okay. Towards infinity. Okay. And this is the name of this is a break in point. Break in point. Okay, so you can get the break-in point from the given graph. What my concern is now is the 20% is the zeta equal to 0.5. okay, which is 60 degrees over here. Okay. So overshoot 20%, overshoot 20%, overshoot 16.3% will give you the zeta 0.5. And this zeta will give you the phase margin of 52 degrees. But we are not concerned about the phase margin. We want to find the angle because this angle, you will use the protector to find the exact point where the intersection between the zeta line and the locus. So this one without using calculator is 60 degrees. Okay. And when it cuts here, okay, so that is your dominant pole. Okay, please remember. So dominant pole from the given graph will be minus 0.7 plus J 1.1. Okay. 1.1. And the gain at dominant pole is using the gain equations, gain criteria. S minus 1. And you replace with the dominant pole value, which is minus 0.7 plus J 1.1. Then we will get the dominant pole 3.36. So I hope you know how to do this using your calculator. Okay. So that is part 1. Part 2 is you have to find the peak time, settling time, and steady state error. Right. So as usual, for part time, sorry, not part time, settling time is you look at the dominant pole plus J 1.1. You know that this one is combination of zeta omega n plus J omega d. And this one is the real part. And this one is the imaginary part. Okay. So this information is very important. 0.7 real part, 1.1 is the imaginary part. So you can find the settling time. 4 divided by real part. Okay. Which is 4 divided by 0.7, 5.7 second, peak time, 5 divided by imaginary, 5 divided by imaginary is 1.1, which is 2.8 second. And from the open loop transfer function, the system type Ty, system type is 0. Okay. So if the system type is 0, there is a position velocity, position error constant exists. Position error constant exists. So how to find Kp from the rule locus? There is no way you can find Kp from the locus, and it's not like a bot plot. So you have to calculate Kp using the final value theorem. Okay. So Kp is equal to limit S to 0. The gain at dominant pole is 3.36 and S minus 1. Then S squared minus 2S plus 5. So you replace S towards 0, then you will get the KP 0.6717 is negative. Okay. And the error is given by 1 plus KP, which is 1 plus minus 0.6717, which will give you the error is 3.04. Okay. So that is part 2. Then find the range of gain K for stability. So to find the range K for the stability, okay, so you have to find the left quadrant, okay, of the local lah. The one that I shaded with this one. What color? This one? Orange. Orange color. This is the range of stability. So you have to find this K, the range of K value, okay, on the orange line. That is a visualization. So, but you cannot get it from the locus. You have to calculate. Okay. The range of K stability is by find the closed loop transfer function. Okay. Again, it is GS 1 plus GS. Okay. So it will be K S minus 1 S square minus 2S plus 5 plus K S minus 1. Okay. And as you know that this one is the denominator is the characteristic equation. S square minus 2S plus 5 plus K S minus 1 equal to 0. Okay. Simplified and organized. So insert inside the root table, plug in the coefficient to root width table, okay, which is S square, S power 1, S power 0, 1, K minus 2, A, 5 minus K, 0, and 0. Okay. So you have to find the K, the A. Okay. So the A is minus 1, K minus 2, 5 minus K, 0. Okay. Over A minus 2. So A will be 5 minus K. Okay. So this one, okay, is a 5 minus K. So we are focusing on this part. First column of the root table must be greater than 0. Okay. So 1 already greater than 0. So the equation left greater than 0 is this one and this one. So we just write the equations. Okay. It's not that difficult. K minus 2 greater than 0. K is greater than 2. 5 minus K greater than 0. So minus K greater than minus 5. Then change the sign. K greater than 5. So therefore, the range of K for stability 0 minus K minus 5. Okay. So finish, and then lastly is to design a controller that could eliminate the steady state error in B2. Okay. So this one also very straightforward. Okay. PI controller. So PI controller generally to reduce steady state error or to improve steady state error. To improve steady state error doesn't mean that to increase. To improve meaning that steady state error meaning that we are trying, okay, to design the controller so that the steady state error is reduced from finite value, any value to 0. Okay. So choose the PI. Any numbers that you like. Okay. GPI. Let's say 0.1, which is near to the origin, divided by S. Okay. This is fine. Okay. For me, it's okay. Then, so the GPI and G together will be K S plus 0.1 S minus 1 S square minus 2S plus 5. Okay. So since the system is type 1, okay, so KP now will be limit S to 0, okay, which is S plus 0.1 S minus 1 S square minus 2S plus 5, okay. So replace zeros. So definitely when this 0, you replace with this S, replace with 0. Everything on the top will be divided by 0. Okay. So it will be infinity. And ESS 1 over 1 plus infinity is 0. Okay. So improve lah. Question number 2. Question number 2. We invite Mr. Amir from TNB to read the question, please. Question number 2A.
The unity feedback system as figure question 2A has a root locus as shown in figure question 2B. The system operates at 25% overshoot. Number 1, determine the dominant poles gain, steady state error, and settling time for the uncompensated system. Number 2, design a PD controller GPD of S, KP, KDS to reduce the settling time by a factor of 2. Number 3, determine the new steady state error and discuss the impact of PD controller on the steady state error. Thank you.
Okay, thank you. We have about 53 participants. Very good. Very good anticipating. Okay. Maybe they're scared of the coming final exams. Should be okay. Right. So now is Q2. Question number 2. So given open loop transfer function. Okay. And then overshoot is 25%, which will give you zeta damping ratio 0.4. But we know that cos theta is equal to zeta. So theta is inverse cos. Okay. Which will give you 66.42. Okay. If we look at the questions, workload is given. Okay. Okay. Workload is given in the red color, right? Okay, so the workload is, sorry, workload, the root locus, I'm sorry. So this is the root locus. Okay. So it is a third order system. So third order system will produce 3 root locus paths. Okay. Which is the first one is this one, towards infinity. The second one is this one, towards infinity. And the final one will be this one, the orange color. Okay. And you have to use protector for the second time. Okay. Tadi first time, now second time you have to using the protector to get the 66 degrees for zeta is equal to 0.4. Okay. This one is a 66.42. Okay. This point is matters because that is the dominant pole. Okay. Clear? Right. So the dominant pole from the reading, okay, more or less will be 1.7 plus J 2.6. Okay. So I repeat again, dominant pole is the built from the minus zeta omega n plus J omega D. Zeta is the damping ratio, omega n is the undamped natural frequency, and omega D is the damped natural frequency. And this one is the real part, and this one is the imaginary part. Okay. So once you know that, so it should be no problem. So therefore, K at the dominant pole is using the gain criterion. Okay. And you replace with S is equal to minus 1.7 plus J 2.6. Okay. Using calculator, so you will get the gain at dominant pole 56.787. Okay. So the real part is 1.7. The imaginary part is 2.6. So from there, you can calculate the settling time. Okay. And again, the system is type what? 0, 1, 2. System type. Anybody's?
1.
Salah.
Zero.
Astaghfirullahaladzim. Tu memang nak kena tu. Type 1 tu. System.
0, 0, 0, 0, sorry. 0.
System type 0. Memang nak kena tu. Okay, so KP lah. Okay, so KP is limit S to 0. Okay. KGS. It divided by the transfer function. So KP is 56.8, 11 multiplied by 5, 1.03. Okay. So the steady state error will be 1 plus 1, 0.5. Okay. Excuse me. So part 1 finish. So part 2 is design the PD controller. Okay. So now is the big thing. Okay, number 2. PD controller. Okay. And the spec is to reduce the settling time by a factor of 2, meaning that TS new is half of the TSO lah. Okay. So TS new is half of the 2.353, which is 1.2 second. Okay. So TS new is equal to 4 divided by real 1.2. So that's why the new real will be 4 divided by 1.2, 3.4. Okay. The new real. Okay, now we find the imaginary part. So how to find the imaginary part? Eh? How to find the imaginary part? So
Input time. Jadi.
yeah, you look here. Okay, this one. Okay, right. That is the real part. So we know that 25%, which is theta 0.4, theta 66.42 degrees. So tangent theta, okay, is equal to tangent 66.42 divided by what? Let's say y lah, the height, okay, divided by y. Sorry, y divided by the new real. Okay, y we don't know. Okay, y we don't know. This one is the new real. Okay, so when you use the trigonometry, so you will get y 3.4 tangent 66.42. Y you will get 7.8. So therefore, the new dominant pole for PD controller is minus 3.4, the real part, divided by the imaginary part, 7.8. Okay, that is your new dominant pole. You need this new dominant pole to find the position or the location of the ZC. Okay. So in order to do that, sketch and calculate the angle. Okay. Which is like this. Okay. Let the new dominant pole as a red color. Set it. Okay. Then the others, which is complex conjugate poles. That's 11. So let's say ZC over there. Okay. Can. Okay. And then draw the dotted line towards the new dominant pole. Okay. And then stated the label the angle theta 1. We are trying to find theta 2. Okay. This one. Okay. Then theta 3 and theta. Okay. Okay. So theta 1 using the trigonometry 7.61 is 45.56 degrees. Theta 3 180 degrees minus tangent 7.76 divided by 1.39, which will be 101.62. Okay. Theta 4, again 180 degrees minus tangent 8.76. Okay. 7.76 plus 1, the length, then 1.39. So theta 4 is 99 degrees. Okay. So the phase angle criterion, theta 3 plus theta 4 minus theta 2. Why minus theta 2? Because theta 2 is zeros. Okay. Zeros. This one is poles. Okay. Theta 1, theta 3, and theta 4 is angle of poles. Theta 2 is angle of ZC. ZC is zeros, equal to 180 degrees. So theta 2 is about 66.2 degrees. Okay. So when you draw the triangle, theta, okay. So this is your x. This is your 3.3976. Okay. So ZC is about 6.81, okay, more or less. And GPD is K S plus 6.81. And the angle, okay, the angle for the at that particular point, okay, is K is equal to S plus 1 S square plus 4S plus 5 divided by S. Okay, replaced with S is equal to minus 3.39 plus J 7.76. So you will get K is about 78.45. So that's why your GPD, okay, is 78.45 S plus 6.81. Okay, where KD is 78.45 And KP is 6.81 multiply 78.45. So KP is 534.24. Okay. Quite long for PD controller. Okay. And then the final one is determine the new steady state error and discuss the impact of PD controller. So for the last part, okay, since the system is type 1, so KP is equal to limit KGS.
Type 0.
The microphone, please.
Bukan type 0 tadi.
Type 0.
Type 0. Baguslah tak tidur. Ingat tidur. Okay. So KP is 7.3. Bila pakai PD controller. Okay. Steady state error is 0.12. Okay. So what is your observation? Previously, this one is after after PD controller. Before PD controller is, what is the error of before PD controller?
0.5. 0.5.
Yeah, ada 0.5 before. And so the conclusion is tu ayat yang mahal expensive sentence is conclusions. PD controller reduce steady state error from 0.5 to 0.12, and at the same time improve transient response, i.e. become faster from slower. Okay. So that is part A. So part B is tuning, Cohen-Kun. So Cohen-Kun is not coming out in the exams. It's already coming out last session. So this session, no Cohen-Kun. So you don't have to study Cohen-Kun. So reduce the load. Okay, so focus on Ziegler-Nichols tuning. Can or not? Okay. Okay, so we continue question 3. Question 3, but the presenter need to have a break for 10 minutes. Can I? 10 minutes break.
And prof.
Okay.
Okay, okay.
Okay. Welcome back to the second sessions. So now we move to question number 3. So I invite okay. Hong Chi Hao, you read question number 3, please. Hong Chi Hao.
In the bot plot, how can the slope of the magnitude plot provide information about the system pole and zeros? Analysis the relationship between the slope magnitude and the type of pole and or zero present in the system.
Okay. Right. This is a theory questions. Okay. So for the theory questions, so we refer to the what do you call that initial slope. Okay. So question 3. EA. Initial slope of gain curve. If initial slope of gain curve is 0 dB per decade, so this one meaning that this is a system type 1. Okay, and system type 1 will be system type 1, system type 0. Okay, will be KP. If initial slope of gain curve is minus 20 dB per decade, so this one is system type 1, which will be KV. Okay, and if initial slope of gain curve is minus 40 dB per decade, those the system type is 2, which will be the KE. So this is very rare, so far 7 years or 5 years ago, this one on the system type 2. Okay, so how to know the order of the system? Okay, so the first order first order system, okay, we can know from the break frequency and the break frequency where the slope is minus 20 dB per decade. Okay. Second order system at break frequency, slope is minus 40 dB per decade. Okay. So same goes to third order. So third order, and the break frequency will be minus 60 dB per decade. Okay. So if a single zeros, so you can see that at break frequency, slope is plus 20 dB per decade, and double zeros at break frequency, slope will be plus 40 dB per decade. Okay, so you have to describe something like this in order to answer the questions. Okay, so question B. I invite Uzair to read the questions.
The bot plot method is a useful tool to determining the transfer function of a system when the complete bot plot is available. Asymptotic approximation plots are often employed to simplify data analysis. Consider the system represented by the given dot plot for magnitude as shown in figure Q.3a. Determining the transfer function for the system based on the provided dot plot. Determining the magnitude M based on the given plot.
Bukan determining, determine. Okay. Right. So now you are given this plot. Okay. This also rare questions. Okay, is a straight line approximations. So by looking at this graph, the system type is 0, 1, or 2. Limit.
Zero.
Zero, because initial slope is 0 here. Can. And then how many break frequency? Jenny Chua.
Four. Four.
Microphone off, please. Jenny Chua. How many break frequency? Jenny Chua tak ada.
Four. Four.
Four. How you get 4? So if you look here, okay. So this start kat sini kan. Then di corner 1. Turun. Di corner lagi. Okay. 2. 2. And straight. Corner lagi. 3. So 1, 2, 3 lah. Okay. You have a 3 corner frequency. Do you understand or not the concept of break frequency? Okay. So this one go straight. This one go straight. Go straight. Okay. Corner. At 0.9. Then go straight. Go straight. This corner again. At 10. Okay. Go straight. Even though 100, the response still goes straight. Until 200, then corner again. At minus 60 decibel. Okay. So the break frequency will be 0.1, 10, and 200. Okay. So question 3B. From the straight line approximation. Good. Break frequency at 3 point. Omega 1. Omega 2. Omega 3. Okay, so you get this one first. 0.1, 10, and 200. And initial slope is 0 dB per decade, which will give you system type 0. But initial magnitude is minus 25.106 decibel. Can you see from the graph? Minus 25.06 decibel. Can you see?
Yes, doctor.
Here. Other. Yeah. Initial. So that one, okay, is that one is equal to 20 log k. Okay. So you want to find the gain key over there. So k is equal to 10 minus 25, 106 divided by 20. K equal to, help me.
0.055.
0.0.
56.
Okay. So now, construct the transfer function, okay, of open loop system with the information of k, omega 1, omega 2, and omega 3. The transfer function structure is ds equal to k s over omega 1 plus 1, s over omega 2 plus 1, and s over omega 3 plus 1. Okay? Can. And from there, you will get 0.056 s over 0.9 plus 1, s over 10 plus 1, s over 200 plus 1. Okay? Then simplify. 0.9 multiplied by 10 multiplied by 200. So finally, the transfer function will be 11.2. Right? Can you check the calculations? Is it correct? 11.2? Is it correct?
I think it should be lower.
This one divided by this one.
1,800.
Huh?
0.056 divided by 1,800. 1,800
Ah,
should be 3.11 times 10 power of negative 5.
I mean the final gain, how much?
Yes, Doctor. 0.056 divided by the second one is 3.11 times to 10 to the power of negative 5.
I don't understand. Huh? Can somebody explain?
3.1 times 10 power of negative 5.
So the total will be, the final gain will be
1 over answer.
this one. Final will be You calculate by yourself, lah. Don't waste time, lah. Okay. So we move to the question C. Question C. This one. Okay. Question C, I invite Dwi Junliang. Dwi Junliang.
Figure Q.3b shows a closed-loop system of a DC motor where RS and CS are the input and output respectively. K is a constant and the transfer function of the system is given as figure Q.3b. The baud plot for the system with K equal to 1000 is given in figure Q.3c1 and figure Q.3c2. Determine the following: the stability of the system, range of K value for stability, and the steady-state error of the system.
Okay, so share. All right. So now Q3C. Okay. So the open loop transfer function will be KGS. Will be 1000 divided by S plus 1. Okay. So both load given. Okay. From the both load system type tu berapa? This one. System type?
Type 0.
Hmm.
0.
Yeah. System type 0, System type 0. Okay. So KP lah. Kan? So the question asks you to find the stability of the system. So stability is find the gain margin. Gain margin. Status. Okay. So gain margin. Okay. 0 dB. Crossed here 0 kan. Kat sini. 1.5 Omega apa tu? Omega PM. And this one minus 180. Dekat frequency over here. Apa tu? 20, 25 radian per second. Omega GM. Fine, So guys, is it correct? Correct,
Yes, yes.
Yes, Prof.
Double check, make sure correct. Okay. So we just write here. This one is 36 decibel at 25 radian per second. This one is 104 degrees positive. At 17, 1.7 kan? Sorry. Radian 1.7 pula. 1.5. Stable. Okay. Okay. And then range of K. range of K value for stability. Okay. So at 25 radian per second. Over here. What is the gain value? What is the gain value? Meaning that we have to somehow shift this one up, okay, in order to achieve marginal stable. So how much we have to shift up? Positive 36 decibel, because the gain margin is 36 decibel positive. To make the system marginal stable, the gain margin is 0 decibel. So 36 minus 0 decibel will be 36 lah, eh? Hello?
Correct, Prof.
Correct. Respond lah. Okay, range of gain K for stability is 20 log K, 36 decibel. So shift up meaning plus 56 decibel So K is equal to 56 divided by 20, so 63.1. Okay. And then total K total, because the previous system is 1000. Multiplied by the shift 63.1. So it will become 63,100. Okay. So therefore, the range of K for stability is 0 K 63,100. Okay. Right. And finally, the steady state error. Okay. So steady state error, we have a two-way, either by calculation or by observation. So system is type 1. Initial magnitude from gain curve is how much? Ni berapa ni? Berapa tu? Berapa decibel tu?
6 decibel.
6 decibel, thank you. And is equal to 20 log Kp. Okay. So 20 log Kp is equal to 6 decibel. Kp is 6 divided by 20. Berapa? 2. Okay. Still. Then the steady state error will be 1/1 plus 2, 0.33. Okay. You can validate by calculation as well. Okay. Can validate. calculation. Okay. Okay, using the transfer function given. Let's say we try to validate. 1000 kan? 1000 divided by 1000, 1, 5, 100. How much? Sama? Okay. Same. Same. Okay. Final one is the D. Using the gain adjustment technique in the frequency domain, GS can be improved to yield a better response. Okay. Determine the value of gain K from the book plot so that the phase margin is 54 degrees. Find the gain margin at this instance. So this is the sampai 50 je. Okay, dia sampai 50 je. So kita kena shutdown dan kita buka yang baru. The maximum 50 page. Okay. Okay, so okay. Find gain K. So that targeted phase margin is equal to 54 degrees. Okay. Previously was previously ideal. Previously was
104.
104. Okay, 104 degrees. Okay, previously. So dia suruh buat the question asks you to do the gain adjustment. So that you get the new phase margin 54 degrees. Okay, so phase margin plus 54 degrees is equal to X minus 180 degrees, where X is equal to minus 126 degrees. Okay. Add phase curve value omega 5 radian per second. You can refer to the graph, which is 5 radian per second. By using omega 5 radian per second at gain curve, at gain curve, you the magnitude is minus 12 decibel. Okay. So shift up the gain curve plus 12 decibel to achieve phase margin 54 degrees. Okay. So therefore, 20 log K is equal to plus 12 decibel. So K is equal to 10, 3.98. Okay. and the corresponding gain margin at this instance is 36 decibel, the previous one, minus 12 decibel, which will be 24 decibel. Okay. Okay, so that is the solutions for the D1. And for D2, okay, explain your observation on the gain adjustment technique, both in steady state error and stability. So meaning that the question asks you to do the comparison lah, before and after. Okay. So so you have to do a little bit calculations on the KP. Okay. So the KP now, find KP after gain adjustment, which is 20 log KP, 6 plus 12, right? dB. 6 is the original from the graph given. 12 is after you shift up 12 decibel due to achieve phase margin 54 degrees. Okay, so it will become 20 log KP, 18 decibel. So KP is 7.94. Okay, and steady state error is 1/1 plus KP 0.112. Okay. And then for the critical gain, okay, GM was 24 decibel. Okay, GM was 24 decibel. And then shift up positive 24 decibel for marginal stable. Okay, which will give you 20 log K, positive 24 decibel. So K is equal to 15.848. And the total of K will be 15.848 multiplied by 1000. The existing gain in the system. So it will be 15.848. Okay. So you can make the table after, okay, terms. Okay, this KP steady state error, K critical. Okay, well, I see better do it like this so you can see where it happens. 15.848. 15.848. This one is 7.94. (0.112). Okay. And the previous one was what? Aidil, tolong. Previous one. Previous KP was 2 kan? Am I right? There is an error. And the range of stability was 63,100.
100.
Right. Can you see? Can you see, guys?
Yes, Prof.
Yes.
So, what is your observation? Miss Chong? Chong, what is your observation? Gain? Adjustment? Reduce? There is the error from 0.33, 0 point, but and decrease ke increase? Decrease the total gain from 63,100 to 15,808. Okay. Wah, panjang soalan. Okay. Okay, guys.
Okay, Prof.
Ada soalan? Any question?
Yes, Prof.
Panjang ni soalan. Aduh. Final exam kan? Aduh.
So yang ni, Prof.
Ya,
Masuk yang ni ya.
masuk. Tak tahulah. Tak tahu. Tak tahu. Kita berehat sebentar. Suara tak ada. Okay. 10 minutes break. Kan?
Okay,
Then,
Prof.
lah.
Okay, Prof. Thank you, Prof.
Last session will be question form. Okay, we continue to the final session, question 4. Okay, question 4. Okay. Question 4. So I invite Bing Han to read the question.
Sketch the magnitude of the book for the following transfer function. Which the function gs 0.5 s plus 1 over s times x over 10 plus 1 times 1 times s over 100 plus 1. The unity feedback system shown in figure Q4b has transfer function gs and the proportional control gcs of 10.
Okay, thank you. Okay, this one simple theory lah. Okay. Question 4. Okay. S dan ya. 10 plus 1. Okay. You replace S with the J omega. Then J omega will equal to J omega over 2 plus 1. And J omega 1. Okay. And from there you can draw the magnitude only. Okay. If you read the questions, just magnitude. Okay. Phase, no need. So start your freehand draw. Okay. Then draw the corresponding diagram for the start from 0.1. Okay. Then okay, 1K. So J omega 2. Okay, J omega 2, which is the break frequency. Dua. So this is plus 20 dB per decade. Okay. Then goes to the slope 20 dB for poles at the origin. Okay. Then goes to the 10. Minus 20 dB. Okay. Then goes to the last one, which is 100. For magnitude. Senang je. Very easy. Okay. Very easy. Okay. That's it. So no need to add up. Okay. So simply you can get direct marks from there. Then goes to the next question, which is B. Okay. Where GCS is equal to 10. Okay. So G overall, open loop transfer functions is just multiply 10 multiplied by 10. Okay. So S plus 2, S plus 2T. Okay. Which will give you 100. And the plot is given, I guess. Okay, plot is given. Okay. So find the gain margin, phase margin. Okay. From the given plot here. So I hope you all understand how to do it. So to make life easy, just draw the 0 dB line. And then just draw minus 180 line. Okay, so that you can see the difference there. Okay. So from here, you dah tahu dah. This one is the omega gain margin. And this one is omega phase margin. Okay, so you read from there. So you can get the values. Okay, gain margin. $25 decibel. Phase margin 53 degrees. 7.5 radian per second. Okay. And the system is stable. Okay, due to the positive phase margin and gain margin. And find the steady state error of the system. So kita, if we look here, okay, slope is minus 20 dB per decade, initial slope. So this one really system type 1,
One.
KV. KV. So you can use either calculation or observations. Okay, so from the graph, let me write for you. From board plot, okay, KV is 1.5 radian per second. Okay, so if we look at the graph here, okay, I delete first. Okay. So this is the minus 20 dB line. Minus 20 dB per decade. Okay, so you use your ruler. Okay. Ikut saja line tu. Okay. And dia cut dekat 0 dB dekat sini. Somehow here. Okay. So that point is 1.5. Okay. Radian per second. That's how you get KV from workload. Okay. So that's why the steady state error is 1 over KV. 1 over 1.5. So you will get 0.667. Or by calculations, you have to calculate the SDS. Okay. S, which is 100 over S plus 2, S plus 30. Okay. So KV, this one cancel out. Okay. So tinggal 100. 2 multiplied by 30. 160. Oh, berapa tu? Yang lain macamnya. Am I right? Saya buat silap ke? Betul? Am I correct? 10 bagi 6.
Bukan 10 tu.
Hmm?
Bukan 10 tu.
Boleh? S plus 2, S plus 30.
10 Doktor. 10.
10.
10.
10 bagi 6. Hello? This one 10.
Ah, betul Doktor. 10.
Oh, ya, 10, sorry, 10.
10 Doktor.
10, dan 10 bagi 60. 10 bagi 60. 1 per 6. 1 per 6 sama dengan?
0.1667.
That one you calculate by yourself, eh? Okay. And then from the question, this one. Okay, it is desired. It is desired to improve the steady state error. Currently 0.667. Ini terkini. Okay. Belum pakai apa-apa lagi. 0.667. So dalam question number 4, you are required to design either LED or lead. So that, okay, so that overshoot 20%, and then the new steady state error is 1/5 daripada yang lama. Jadi 1/5 darab 0.667 lah. Kan? Macam itu. How much? New steady state error is 1/5. How much?
1.2.
Tadi tu berapa nilai? 0.667 kan? 0.667 divided by 5.
0.113.
133.
0.133.
132. Okay, the new one. Ni tadi KB kan? KB ni betul 100 ni, sorry. Ni betul tadi. Okay, so you akan dapat sini 1.667. So the steady state error will be 1/1.667. So lebih kurang dapat 0.6. Okay, ni betul. Okay, so sekarang ni this is target. The new steady state error. Reduce lagi lah daripada 0.667 sebanyak 5 times. Okay, with the overshoot 20%. Okay, so overshoot 20%. Okay, will give you from the graph 0.46, and the targeted phase margin will be 48 degrees. Okay. Jadinya, if we look here, the ESS is equal to 1/kV, okay, which is 1/, not this one. Sorry. Tadi dah buat kan? Okay, 48 degrees. Jadinya sekarang ni kita nak buat lag compensator. Okay, lag compensator. So for lag compensator, dia punya prosedur dia apa? Prosedur. Okay. Prosedur dia adalah kita kena tambah dia punya targeted phase margin. Yang ini adalah tadi tu ni, sorry, 48 degrees plus 10 degrees correction factor. Okay. Correction factor. So kita kira lah dia punya phase margin tu. Okay. Untuk mendapatkan 10 degrees. Okay. So dia punya frekuensi dia lebih kurang pada omega 1.7 radian per second. Dan satu decade dia punya ZC adalah 0.17, which is 1 decade before. And PC is 0.02 radian per second, which is ini lah, ZC 0.17. PC 0.02. Ini adalah minus 20 dB per decade. Okay. So the lag compensator transfer function 1 over ZC plus 1, 1 over PC plus 1. Okay. Which is ZC greater than PC dalam lag compensator. So 1 over 0.17, 1 over 0.02 plus 1 plus 1. Then you simplify, you will get 0.1176 S plus 0.17 S plus 0.02. Okay, so sampai sini saja cukup for lag compensator. So after this you can try for lead. Sebab question ni kata boleh juga untuk lead untuk mencapai spec design tersebut. So this one I leave it to you, okay, to do the lead compensator. But for lead compensator, you make sure that ZC is less than PC. Okay, so itu adalah syarat bagi lead compensator. Okay, I guess we stop here. Okay, very tiring, about 2.5 hours class and revisions. If we have time, we can discuss for the last 2 sessions if we have time. Okay, we can set another time for last 2 sessions if needed. So I wish you good luck for the final exam on Thursday. Okay, and this lecture is recorded and will be distributed to the WhatsApp list. Thank you for your listening and I wish you good luck. Bye.
Thank
you,
you.
Prof.
Thank you, Prof.
Thank you, Prof.
Bro.
Have a good weekend. Bye, Prof.
Thank you, Prof.